stereoisomerism. Stereoisomerism can further be divided into two types. What are these types? You can either have configurational isomerism or conformational isomerism. Configurational isomerism can further be divided into geometrical isomerism and optical isomerism. So what are these types? Let us begin. First of all, if we talk about stereoisomerism is basically the isomers which have different spatial arrangement. That means the arrangement of the molecular formula is same, the structural formula is same, only the spatial arrangement, that means the arrangement of groups in 3-dimensional space is different. For example, one compound has a group attached like this and another compound has this group attached like this, and such two different arrangement of groups in 3-dimensional space can also give rise to different compound. Such compounds which have different arrangement of groups in 3D space, different spatial arrangements, such compounds are called as stereoisomers. Further, if we break them down, we have configurational and conformational. Conformational or conformers isomers or conformational isomers are basically due to different arrangements which arise due to free rotation across single bond, because across single bond the rotation is free. You can have, let us say these are two carbon atoms in ethane, and you can have different arrangement. One arrangement is this, another is this, another is this, another is this. So each one of these represent a unique conformer or unique compound. So these different arrangements can be huge in number. So if anybody asks you how many conformers are possible for ethane or for that matter any compound, the number of conformers for any compound is always infinite, because number of possibilities are infinite. So that is why we never count conformers, right. Now we come back to configurational isomers or geometrical and optical. Configurational are basically the compounds where you have either geometrical isomerism or optical isomerism. Geometrical isomerism arises due to restricted rotation across double bond. If you have a double bond between two atoms and the groups attached to double bonded atom must be different. First condition for geometrical isomerism is there should be a presence of double bond. So first condition is double bond, because geometrical isomerism arises due to the presence of, first condition is double bond, and the second condition is different groups on double bonded atom, For example, if I give you two examples, I have C double bond C, this one, and I have another compound, this one, and another compound, this one. So out of these three, 1, 2 and 3, what do you think, which one will show geometrical isomerism? This has double bond, yes, first condition is met, but second condition, different groups on double bonded atom, no, second condition is not met, because these two groups are same. So it will not show GI, or geometrical isomerism is not present in this compound. Here Cl and H are present, two different groups are there on this double bonded, but this double bonded carbon has same hydrogen atoms, so same groups on the carbon, so it does not show geometrical isomerism. Third one, yes, third one shows geometrical isomerism, because double bond is present and groups attached to double bonded carbon, hydrogen and Cl, different groups on this double bonded carbon, and another double bonded carbon also has two different groups. So both the conditions are met here, that double bond present and double bonded carbon has two different groups. So this shows geometrical isomerism, whereas first and second does not show geometrical isomerism. So this is how you figure out whether a certain compound will show geometrical isomerism or not. Alright. So we have discussed this, and here we have another example where we have taken double bonded carbon atoms, one side C2H5 and H, another side both hydrogen atoms. So you can check C, same groups are present, so it will not show geometrical isomerism. So that is it for now. Thank you.